Hello, all. Good morning. So, this is Parth Joshi again. So, can we get started?
Yes, we can start.
Okay.
Yes.
Sir, I am sharing my screen. So, can you please confirm whether you can see my screen?
Yes, I can see.
Okay.
Yes.
And so are you able to see changes in slides?
Yes.
Okay.
Yes, I can see.
Sure. Thank you, sir. So, I hope the recording has started. I started it from my end. Uh,
Yes,
okay.
it is
Okay.
started. Yes.
Okay. Thank you, sir. Yeah. So, good morning, all of you. So, I am Parth Joshi. So in in yesterday's session, so we looked at uh, like the basic context of like the current Indian scenario. What are the current issues that are being faced, uh, like uh, the crude oil prices and like the India's dependency, like import dependency on crude oil and natural gas, and also the issues like the air pollution and global warming, which are causing a lot of concerns over which for which so the transition to electric mobility is being proposed as a promising option for curbing the adverse impacts of the transport sector on uh, the environment. And we also looked at what are the initiatives taken up by the government of India, such as FAME India scheme, the phase one and phase two, and what are the possible benefits that can be estimated if this particular policy was implemented as planned. So we see that this policy, the benefits are quite promising. Then later on, we looked at uh, the basic, like the functional requirements of any particular automotive transmission, and then we looked at why do we need a transmission in a vehicle. So we need a transmission to basically match between the power source and the load. So the transmission will be allow us to manipulate the operating point of the power source in such a way that we deliver the required power at the required vehicle speed, and we are also able to operate the power source efficiently. Then we looked at uh, the comparison between conventional and electric powertrains, particularly with a particular focus on the power source, basically comparing IC engines and electric motors and their typical characteristics. So we saw that uh, IC engines always generally need multiple gear ratio transmissions. Uh, so whereas an electric vehicle, uh, because of the particular characteristics of the electric motor, uh, so we can have a electric motor along with a single speed transmission, so as to provide the same performance or similar performance as that of a conventional vehicle. So now we like in order to design any automotive transmission for a particular vehicle, uh, so we need to look at uh, what is the power requirement. So, so while defining any particular application, so there are certain requirements that are laid out. So in terms of probably rated power, or uh, what is the maximum vehicle speed that it should be able to achieve. What is the uh, maximum road inclination that or road grade for that matter that it can climb. So for designing transmissions for any particular vehicle, so we first need to look at what is the load or what is the power demand. Uh, so for that, we need to look at the vehicle dynamics. So in today's session, we will basically cover the equations of longitudinal vehicle dynamics. Uh, so, uh, so for simplicity, we will be looking at only the longitudinal vehicle dynamics behavior. Uh, there are several forces that act on a vehicle during its motion. So to start with and to estimate what are the power requirements, we'll first just consider longitudinal vehicle dynamics, which means that so when the vehicle is moving along a straight road, uh, so for that case, uh, what are the kind of forces that act on the vehicle in that scenario, and then we will try to estimate what is the power requirement so as to propel the vehicle at the required speed. So, so any one of you already familiar with this part like of vehicle dynamics? So have you learned this already, or is this new to you? So any feedback on that? Hello. So can anyone tell me whether have you learned these concepts already, or have you like are you already familiar with these things?
Prerna, Sital, Kshitij, Kshitija, Kunal, you have to talk. Pratik.
So,
Hello.
Hello. Am I audible, sir? Like,
Yes, you are
yes,
audible.
okay.
So I request students to answer.
yes, sir, we have already learned it, but it would be better if you could go with again.
Okay. Okay. Fine. Fine. So, like as per my understanding, I had just as per my knowledge, I had prepared like for this particular session. So hopefully, like whatever I have covered, it would reinforce whatever you have learned already. And if some of you are not familiar with this, I think it will be helpful for you as well. So we'll start with this particular aspect of longitudinal vehicle dynamics. So there will be different forces acting on the vehicle. So there will be propulsive forces which try to propel the vehicle forward. So so these forces arise basically due to the power source that like the IC engine or electric motor, and these propulsive forces act at the contact between the tire and the road. So this force Ft, which is shown over here, that is basically the propulsive force. And there are forces which resist the vehicle motion. So, so they are basically can be categorized into three types of forces. So one is called as the wheel resistance, which is resistance to the wheel motion. Then the air resistance. So whenever the vehicle moves in any fluid or any object, when it moves in a fluid, then there are forces which act which opposite to the motion of the body. So air resistance is a force which represents the aerodynamic drag. Uh, then gradient resistance is another force. So whenever a vehicle moves along a slope, so then there is a certain component of the weight of that body itself which acts in a direction opposite to the motion. So here in this particular diagram, we can see that the weight, so this vehicle is moving on an inclined plane. So that if we resolve the weight uh, in directions like along and perpendicular to the motion, so then we can see that there is a component acting along opposite to the direction of motion. That is called the gradient resistance. So now we will see each of these forces in more detail. So first we look at the wheel resistance, which is also called as rolling resistance. So it is basically the resistance to the pre-rolling motion of any wheel. So this force arises because of the particular material behavior of a tire. Uh, so tires are made of like rubber, which is viscoelastic kind of material, which so because of this the particular behavior of the tire and the deformation of the tire, then that is how this force arises. So normally, if we like have a properly inflated tire, so and yeah, sorry for the bad circle. Um, assuming that it's a circle. Uh, so if we have a properly inflated tire and if it is lying at rest on the road, like let us say this is one of the tires and let us say the vehicle has four car tires. So then there will be a certain portion of the tire which is in contact with the road. So it will be a certain small area of the tire which will be slightly flattened out like the way it is shown in the picture over here. So then there will be a certain pressure distribution. Basically, the ground will exert certain forces on the tire at the contact patch. So let us say this represents the pressure distribution. So what can we comment about this particular pressure distribution? Any guesses? What will be the nature of the distribution of this pressure exerted at the tire contact patch? Any ideas? So here the vehicle is at rest and there is no driving torque that is acting on this uh, particular wheel. So in this situation, what will be the nature of the pressure distribution? So any ideas? So it will be basically symmetric with respect to this particular axis, vertical axis. So the pressure distribution is equal on both sides of this particular axis, symmetric. So now, one if the wheel starts rotating, then what happens is that uh, the portion of the tire which is in like basically the part which is in the front side, like so if this is rotating this way, like this is the direction of rotation, then the part of the tire over here, it is in compression, so it is being compressed, uh, and here once this part of the tire goes like outside of this contact patch, then there is the compressive force is released. So then in this particular uh, zone, so there is certain part where this particular is portion of the tire is being loaded, and in this part is being unloaded. So the particular rubber or material of the tire, there is a certain behavior which is called as hysteresis. So you might have studied this earlier in other contexts. So So hysteresis is where, like, if you, let us say, if this is the uh, force versus displacement, force versus displacement kind of curve. So if this is the pattern, like how the force increases as we let us say if we deform a spring, then if it is a non-linear spring, let us say, then this would be some arbitrary pattern in which the force increases with the increasing displacement or deflection. Now, when the spring is unloaded, it will uh, follow the same kind of unloading path when as we release the force or release the load from the spring. It will be as it gets unloaded, it will follow the same trajectory. But in the tire material, there is some hysteresis. So there is certain loss of energy uh, involved in the material. So when it gets unloaded, the force during, like the load during that is it experiences during unloading is somewhat lesser than what during loading. So there is a certain energy loss in every loading and unloading cycle. So that is called as hysteresis. So that uh, gives rise to some kind of an asymmetric pressure distribution. So you can see that this particular pressure distribution which is shown over here. So it is actually asymmetric. So during loading, uh, the pressure that is exerted over here is like more, whereas during unloading it is actually lesser. So then, because of this particular nature of like asymmetric pressure distribution, there is the net resultant of force, if we call it as R, it is kind of displaced by a certain distance E with respect to the wheel axis. Uh, so there is a certain eccentric kind of a load. So in the figure shown over here, GR is the load acting on the axle, whereas R is the resultant reaction from the ground. So because like if the vehicle does not experience any acceleration around this vertical direction, so then these two forces like GR and R will be in equilibrium. So which means that R will be equal to GR. So on a level surface. So so if we uh, like look at the behavior of this force R versus GR, so then they are equal and opposite, but there is a certain distance like E over which they are separated. So then that gives rise to a certain couple, so or moment, uh, which is opposite to the direction of the motion or opposite to the driving torque. So if TR is the driving torque, so the moment that will be generated, it will be, so here if TR is clockwise, the couple moment will be anti-clockwise. So the what will be the moment of due to the couple? It will be R into E. So this is the opposing couple. So that is basically the rolling resistance. So this particular couple can also be equivalently expressed as a force. Let us say F R roll. Let us say what which is called, so which is the rolling resistance, which acts let us say at the axis of the wheel. So this rolling resistance force into the wheel radius. So that, let us say if this particular force acts at this axis, so then the moment of the couple and whatever more effect that is produced, like the moment if we calculate the moment about, let us say, this point, then the effect by this thing is essentially the same as what would be produced by the couple. So if this is the rolling resistance force, if we call it, so then that acts uh, over here. So that is equivalent to the couple moment. So now if we write, like, calculate the moment about this point, uh, so if so here Fu would be the force that is acting at the tire ground contact patch. So if you calculate the moment about the axis of rotation, let us say, so then the moment about the axis of rotation is this Tr, which is equivalent to uh, the moment produced by this particular force about the axis Fu. So Fu into the radius of the tire and Re, which is basically the moment due to the couple. So these two are in equilibrium if it is not accelerating. If suppose if the vehicle is moving at a constant speed, then this is the kind of equation that we would get. Now, if the wheel is rolling without any load torque acting, so if TR is 0, so then the relation that we would get would be this force Fu. So basically this RHS will be 0. So then Fu would be equal to minus Re divided by this R dynamic. So this R dynamic, R dyn, is basically the dynamic wheel radius. So it is not exactly equal to the the complete tire radius, because this tire is being flattened out over here. So this is the distance from, like, the axis to the tire ground contact patch, which is called as the dynamic uh, wheel radius. So it's an important tire specification. So that's how basically we calculate this rolling resistance force. So so now if we look at this rolling resistance force, it is basically E by R into GR, which is the ratio between, like, ratio of this eccentricity to the dynamic radius. So this rolling resistance force is proportional to the axle load, and this constant of proportionality is called as, let us say, Fr, which is the rolling resistance coefficient. So this rolling resistance coefficient is an important, again, an important tire specification, and that has a significant impact on the power consumption of any vehicle. So this particular the value of this rolling resistance coefficient depends significantly on the nature of the road, and also it depends significantly on the tire pressure and the tire material, and basically the kind of material of the, like, the what is the nature of the road and the tire material, and what is the uh, the interaction between the tire and road. Now if the vehicle is moving along an inclined plane, then the axle load will be acting like vertically downward, and let us say alpha is the angle between the uh, the normal reaction and, like, the normal to this particular surface and this vertical load. So now this the value of this particular reaction force R will be equal to this, the component of this force along this direction. So it will be GR into cos alpha. And so if we from the previous particular derivation, if, like, similarly, if we try to derive the rolling resistance force, it will be come out to be Fr into mg cos alpha. which is the component of the weight along this direction of like normal to the inclined plane. So this rolling resistance coefficient is found to be approximately constant for low speeds. So normally we do not encounter very high grades. So generally the road slope is gentle, and if so the gradient is expressed as a percentage. Uh, so it is basically tan alpha expressed as a percentage. So if the grade is generally like 10% or lesser than that, then the value of this alpha is about 5.7 degrees. So because of this small angle, so the value of cos alpha is nearly 1. So we can like for practical purposes, we can actually ignore the effect if it is gentle grade. Now, how do we calculate this value of rolling resistance coefficient? So now let us say if we have a passenger car on a concrete road, so then empirically, like from research, it has been found that this is a good fit. Uh, so so this expresses the behavior of the rolling resistance coefficient with vehicle speeds. Uh, so for like low vehicle speeds, it's like somewhat nearly constant, uh, if not. And as the vehicle speed increases, it will rapidly increase its speed. Similarly, there is another empirical relation for passenger cars on a concrete road. And here the vehicle speed VF is in kilometers per hour. So this is another expression that we can use for calculating the rolling resistance coefficient. So if we look at the typical values of rolling resistance coefficients, for a smooth road surface, smooth concrete road, we can like observe the value of rolling resistance coefficient about 0.01. And for different types of roads, we see that the value of the rolling resistance coefficient varies quite a lot. So if the road like material is like the road is kind of soft soil or sand or something like that, so then the rolling resistance would be much more. So we can imagine that. So then that's why we can see that it's like the rolling resistance coefficient is significantly higher in these cases. So up to this point, is everything clear? Are there any doubts? Any questions on this? So I encourage all of you to please participate in, and so if you have any comments or doubts, if you can like interrupt me at any point of time and ask like any question. So you need not wait for me to ask whether you have a question or not. So can we proceed?
Yes, sir.
Okay. Yeah. So another force is the air resistance. So when a body moves through any fluid, let us say if the car is moving through air, then so while moving through the air, uh, because of the motion of like or and the particular shape of the vehicle, there is a certain amount of air that is being displaced, or so the vehicle pushes some air like aside, and then creates so when the vehicle moves forward, whatever air that is being like was displaced by it, So let us say the air was pushed out when it was like just if the vehicle was, let us say, here, then the air was pushed out. So when it has moved forward, so now this air will try to come back into this zone. So then there is a kind of vacuum, or let us say a low pressure kind of region that will be created over here on the backside of the vehicle, whereas this air in the front of the vehicle is pushed forward. So so then that creates a higher pressure, like it tries to compress the air. So then there is a high pressure zone created in the front of the vehicle. So so considering the pressure distribution, so there is a net force opposite to the direction of the motion. If this is the direction of the motion, so considering there is a high pressure over here and low pressure over there, so that is called the shape drag, which is opposite to the motion. In addition to that, there is also skin friction drag. So, so have you learned boundary layer theory and all that in fluid mechanics? So, like if you consider like any body or any plate, something like this, and the fluid is moving onto it. So there is a certain thin layer where, like the thin layer of, let us say, air molecules or the fluid, uh, where there is a certain in this portion of the this thin layer, the viscous force will be dominating, and because of the viscosity, the air molecules in contact, immediately in contact with the surface, will stick to the particular surface, and they will cause a certain amount of friction. So adjacent layers will try to slide on top of this, and because of the viscosity, so it will cause a shear force between different layers of the fluid, and that will lead to a force again opposite to the direction of the motion. Uh, so here it will again create forces opposite to the direction of the motion. So that is called the friction drag. So for any body, the total drag force, like in combining the shape drag and skin friction drag, that can be expressed as this particular force. So it is half rho into AF into CD into this BF minus VW. So rho is basically the density of the fluid, which is air over here. AF is basically the frontal area. So frontal area is, let us say, if this is the direction of motion, so then the area projected on top of the plane which is perpendicular to the direction of motion. So let us say if the car looks something like this, like from the, if we see from this side, so the car, looks something like this. So this is the, like, if we cut the vehicle like this, so this is how it would look. So the area of this out from, like, considering this outer boundary, so what is this particular area? So that is called the frontal area. And this is basically the drag coefficient, which is the net effect of this shape drag and skin friction drag. And Vf is basically the vehicle speed minus wind speed. So Vw is basically the wind speed. So let us say if the wind speed is like this, again in the direction of motion, so then Vf minus Vw is basically the relative motion between the fluid and this vehicle. So this is basically the relative velocity. So this is how we can express the air resistance. So any questions on this? So if we look at the typical values of the drag coefficient for different kinds So let us say if it is a motorcycle with a rider, then uh, generally the drag coefficient will lie in the value in its range around 0.5, 0.7. If we have a flat plate, which is in opposite like direction of, then the drag coefficient associated with this is nearly 1. So if we have a small smooth geometry and a small frontal area, then you would generally tend to have a lower drag associated with that. So generally companies try to make the shape of the body as aerodynamically efficient as possible. So let us say we consider these vehicles, like let us say this passenger cars like Mercedes or Porsche. So they have a relatively lower uh, drag coefficient, like about zero point 0.3 or so. Whereas buses generally are like a flat plate kind of a geometry. If we look at the frontal area, so then the drag coefficient would be substantially higher, about point even up to zero point 0.8 or so. Because of the kind of box type of shape that the bus body has. So these are the typical drag coefficient values for different categories of vehicles. So another force that we encounter is the gradient resistance. So when the vehicle moves along an inclined road, let us say alpha is the angle of inclination. So the weight of the vehicle would always act in a vertically downward direction. So if we resolve the force, like the weight in a direction normal and along the inclined plane. So there is the component of the weight which is along the direction of motion is mg sine alpha, and in this case, because it is moving up the road, the component of the weight is actually opposite to the motion. So that also causes some resistance to the motion. So if the vehicle was moving downhill, so then this particular component of the weight will actually act in the direction of the motion. So this will actually assist the motion. So these are some like typical gradients that we encounter. So these are for Europe. So we like these are the maximum road gradient that we can encounter in these kind of these some of these countries like Germany or France. So there are some cases where there are steep slopes like 26%, but typically uh, even a gradient of 10 to 12% is also considered very high for a vehicle to climb. So now, till now, we have seen what are the resisting forces, so which includes the wheel resistance or rolling resistance, then the force due to the gradient, and also the air resistance. So now, if we try to write the equation of motion of this particular vehicle, so we will apply Newton's second law. Um, so here we consider this vehicle as a lumped mass with some mass m. So so the mass into the acceleration uh, will be basically the net force acting on the vehicle. So which is the difference between this tractive force acting at the wheels, which arises due to the power source, and this is the resisting forces. So here we introduce a factor lambda. So since we are considering this particular like vehicle as a lumped mass, um, so then we also incorporate the effect of inertia of rotating components. So there is certain amount of inertia and there is certain amount of work done in rotating these components like the IC engine, transmission, and differential. And so there are many rotating components throughout the vehicle, like throughout the drive line. So, so if we calculate uh, the inertia of the all these rotating components and reflected onto the axle, uh, so if we call this particular as sigma j uh, as the total deflected inertia, so which represents the equivalent inertia if at all, like there was a cylinder and the inertia of that cylinder like along the axle, uh, if it were kind of equivalent to all the rotating components together. So how do we find this reflected inertia? So EV basically establish an equivalence of kinetic energy. So let us say, so kinetic energy of this, uh, let us say rotating cylinder, which has this equivalent inertia, will be equal to the total kinetic energy of all the rotating components. So then, because of the different speeds associated with for every rotating component, because of the gear ratios, so then the angular velocity of each of the component will be different and the inertia will also be different. So if we add up all these together, we will get the overall kinetic energy of this system. And this is equivalent to the kinetic energy of this cylinder, rotating cylinder. So then that's how we get the equivalent inertia. So that divided by the, this particular mr square factor. So, so that is how we calculate this particular factor lambda, which incorporates the effect of the inertia of rotating components. If we have to calculate the tractive power, so that will be the tractive force multiplied by the vehicle speed. So this is the tractive power required, and this is the tractive force that would be arise considering like if the uh, if the vehicle has to uh, be if, to propel the vehicle at a certain speed. Now, if we want to calculate what would be the tractive power available or tractive force that is that can be achieved considering the with respect for any given speed, so we can calculate using these expressions like considering the efficiency of the drivetrain and what is the max like the power that can be delivered by the power source. So that power divided by the velocity, that is basically the force like multiplied by the efficiency. So that would be the force that is available. So considering if this uh, force, like let us say for certain cases, uh, for propelling the vehicle at a certain speed, the power available might be something, and if propelling the vehicle at that speed requires certain power higher than what is required. I mean, I'm sorry. So if the power available is lesser than what is required, so then the vehicle will not be able to achieve that speed in that case. So we looked at the equation for calculating the rotational inertia coefficient, which is lambda. So this particular graph shows what are the typical values of this coefficient for like a passenger car. So considering the typical gear ratios associated with, like let us say the first gear, second or third or fourth. So for a typical passenger car, like the first gear ratio would lie in this range, and whereas second gear lies in this kind of range. So the typical range in which this inertia coefficient lies is about from 1.1 to 1.5 for different gear ratios. So this envelope gives us the broad range in which this value of lambda will lie. for different kinds of passenger cars or different vehicles. So this gives us an idea like for different like in different gears, how significant is the effect of inertia. Uh, so let us say in the first gear, the uh, the the gear wheels that are required to provide that the higher gear ratio. So so then there will be substantially bigger gears that are required uh, for this particular to achieve that gear ratio. So then that has a higher inertia associated with that. So the inertia scales as r square, mass into r square. So then that uh, so as the size of the gear increases, so then the inertia will significantly increase. So for the lower gears, the inertia effect is like much more significant, whereas for the higher gears, let us say four gear or if we have even a fifth gear or so, then the inertia may not be that significant. So, so any doubts on this? Any questions or comments on this up to this point? So at least you can respond whatever, like if you don't have any doubts as well. Hello.
No doubts, sir. No doubts, sir.
Yeah, fine. Yeah, thanks. So if we try to calculate the tractive force requirement for and how it varies for different vehicle speed and road gradients, we will get a plot like this, the way it is shown over here. So how do we get this plot? Uh, so we calculate all the resisting forces. So we calculate the rolling resistance force, air resistance, and also the resistance due to grade. So the rolling resistance force is largely independent of the vehicle speeds for lower speeds. But as we looked at what is the rolling resistance coefficient, right? So it so for like let us say this particular expression, so we saw that this so for low speeds it's like somewhat constant, and then later on it increases rapidly with greater vehicle speeds. So that would be the nature of the rolling resistance force, which is this particular force Fr, let us say. Then the air resistance force is directly proportional to V square, or the velocity square. So then, so there is a quadratic uh, nature. So the parabolic nature of this particular rate of increase of the air resistance. So we can see that these kind of curves are parabolic in nature, or somewhat like that. So and so with increasing gradient resistance, we will get we'll need significantly higher and higher amount of attractive force required. So for different grades, so the gradient resistance will be independent of the vehicle speed. It only depends on the road inclination and the weight of the vehicle. Uh, so we neglect the reduction in the weight of the vehicle as it moves through uh, at constant speed. So so for for any vehicle, we can calculate the tractive force requirement. So let us say like if we increase the gradient, so like we will see progressively higher and higher curves like this. So starting from zero gradient up to, let us say 15% gradient. So we see that how the tractive force requirement increases with respect to vehicle speed. Similarly, we can also calculate the power requirement. Uh, so and its variation with respect to vehicle speed. So it's basically the tractive force into the velocity. So we may get curves something of this kind of a nature, which is shown over here. So we looked at what are the tractive forces and resisting forces. Uh, so now, so yeah, so this particular graph that was shown, it was for constant vehicle speed. So like, so the acceleration, let us say m dv by dt is basically the um, net force. So that will be zero. Uh, so so the tractive force will actually be equal to the resisting force. So let us say T minus, let us say F R, let us say the total resisting force. So that will be equal. Uh, so it will be equal to zero. So then the tractive force exactly balances the resisting forces. So in this, so this plot basically shows this type of characteristic. So, so the sum of the resisting forces is what is being provided by the power source over here. So as I mentioned earlier, uh, so there is a like maximum force that can be transmitted by the tire and road surface, like the contact patch between the tire and road surface. So it can withstand a certain amount of like maximum force, which is governed by the adhesion limit, or basically there are adhesive forces at the contactive patch, uh, which kind of are responsible for this particular propulsive force. So then this particular limit of adhesion is uh, given by a tractive force coefficient or static coefficient of friction. So like normally we will have the static wheel radius, uh, which is basically the distance from the center of the wheel to the road contact plane when the wheel is at rest. And we have a dynamic wheel radius, as I mentioned earlier. So the distance between the axis to the tire road contact patch. Uh, so, uh, so we have a phenomenon which is called as slip. Uh, so, so because of the deformation of the tire material, so if it is like a, let us say a freely rolling wheel. So let us say if this is a uh, rigidly rolling wheel, and this is traveling on a certain flat road, let us say. So there is no, assume that there is no slipping over here. So the velocity of the center of mass would be r into omega. So where omega is the angular velocity of this uh, wheel. So what would be the distance that is traveled by this particular wheel in a certain amount of time t? It will be r omega into t. So but what happens in this kind of wheels with rubber tires? So so because of the particular deformation of the tire material, it ends up traveling a distance lesser. So let us say if the actual vehicle speed is v. So there is a certain like distance by which, like because of the loss of energy due to the elastic deformation of the tire. the vehicle ends up traveling lesser distance than what a freely rolling tire of this dynamic radius would. So then there is a certain difference between the actual vehicle speed and this R omega. So that is called as wheel slip. So during traction, uh, the vehicle actually ends up traveling lesser distance than what predicted by the actual vehicles uh, by the angular velocity. On the other hand, if we apply brakes, then the vehicle ends up traveling more distance than what we would have like expected as per the angular velocity. So the actual vehicle speed is greater than r omega, whereas here the actual vehicle speed is lesser than r omega. So, uh, so this particular maximum tractive force that can be supplied by this tire rod contact patch, it depends on the extent of this wheel slip. So these are some typical static coefficient of friction, uh, which so if we look at this, so like consider the road reaction as like R, then the maximum tractive force that can be supplied by this tire road contact patch is equal to this mu into R, where mu is the static force coefficient, like static friction coefficient. So for a dry road surface at a certain speed, let us say of 50 kilometers per hour, the static coefficient of friction is about 0.85. So depending on the nature of the road and the speed of the vehicle, this particular coefficient of friction will vary. So when the tractive force exceeds like whatever so for a certain vehicle speed, if the tractive force requirement exceeds whatever that can be supplied because of the like adhesive capability, then the wheels will start slipping on the ground. So this is especially observed when during the rainy season when the road becomes wet. Then we can see that the tires actually start slipping, uh, and even on icy roads or snow covered roads, or even on sand or soft roads. So we see that um, those kind of roads do not have the much capability to supply uh, like much tractive force. So then in that case, because the road cannot support much traction, then the wheel starts slipping. So similar to the rolling resistance phenomena, so the tire tread, because of the particular motion of the wheel, the tire treads in the front they get compressed, whereas the tire treads behind they are in like being released or unloaded. So this asymmetric pressure distribution also gives like corresponding shear force, shear deformation in the side walls of the tire. So which gives rise to this particular force Fx, which is the tractive force. So as I mentioned, like the because of the asymmetric pressure distribution, we get different this particular tractive force like the shear component like this, and also this eccentrically like displaced uh, force component like Pz, which is displaced by this distance a from the axis. So we saw what is the wheel slip, and so this particular graph shows how the like basically the ratio, this coefficient of static friction, or this tractive effort coefficient. So how does it vary with respect to the normal load? So let us say this reaction force is R. So this ratio F, like where F is the tractive force. So how does it vary with respect to the wheel slip? So for initially for very low values of slip. Uh, then in this particular region from O to B, the tire behavior is more or less linearly elastic. But beyond this particular portion, as with increasing slip, uh, the tire is able to supply lesser and lesser tractive force. So at this particular point, it's like 100% slip. So that basically depicts like, so it shows that the tire contact can support with much lesser force than this particular. So this is the optimum slip value. So this is associated with the linear elastic deformation of the tires. So for different natures of road and so let us say asphalt or concrete roads. So generally we see these peak value of this tractive effort coefficient as about 0.8 or 0.9. So whereas when it is slipping, it's about 0.75. So whereas on the other hand, like for ice, it's as less as 0.1 uh, during so the peak value itself is 0.1. So we can see that on an icy kind of road, the tires would largely spin uh, very fast because of this tractive effort coefficient. So we saw the different propulsive and resistive forces. So if we combine them into this equation of motion, uh, so this is how we get the overall equation of motion. So up to this point, are there any questions or doubts? So if not, so, so I'll give you an activity. So let us derive the expressions for the axial reaction forces. Uh, so let us say if this vehicle is moving along this inclined kind of plane, and you can consider this particular notation which is given in the figure over here. So I hope this figure is clearly visible to you. Uh, so you are like, so we just explained, like we just saw what are the different forces acting on the vehicle, and so the resisting forces as well as the tractive forces are shown in this particular figure. And we also have the uh, reaction forces like this. WF is the reaction force on the front wheel, and WR is the reaction force on the rear wheels. So now the task is uh, to derive the expressions for these axial reaction forces, and then find out further what are the expressions for the maximum tractive force for a front wheel drive as well as a rear wheel drive vehicle. So, so I'll give you some time, maybe 5 to 10 minutes or so. So first so I like request all of you to work out uh, the values of this front and rear wheel reaction forces. So what you have to do is a simple, uh, like simple rigid body mechanics. Just apply 11th standard physics to this thing. So we have already derived the equation of motion. So I hope you have noted down that. So
Yes, you can give 10 minutes, 5 or 10 minutes, so that they will work out on it. And then you can ask any one of them to share their screen so
sure,
that
sir.
you can discuss the solution and you can check whether it is correct or not. So
Yes, sir.
again, like I'll repeat that you take 10 minutes, 5-10 minutes and solve this. Again, we will start after 5-10 minutes. Okay.
Right, sir. Yeah, so if any one of you have any doubt on how to derive this thing, or if you want me to show the equations for any of these things like earlier, so let me know. So otherwise, you can proceed and derive the expressions for the axial reaction process. So, are all of you available till around 10:30? So that like I have still more some part to cover for today. Yeah, so please respond like are all of you available till 10:30 today? So I have about half an hour left to cover. Hello. So it's about almost the end of 10 minutes. So are like any one of you has completed deriving these expressions for axial reaction forces? Uh, so I'm expecting a response from all of you. So at least let's say what if you have completed, say yes, or if you need more time, ask like say that you need more time, whatever. But at least there is just a silence. I don't know what is happening.
Sir, I've completed.
Okay. Yeah. So can you share your solution? So you can just take a photo or something like that and share your screen.
Sir, can I just share the final expression photo?
Yeah, sure. Sure.
Okay.
No, you can actually share like how you derive that. So I'll just stop sharing from my side.
Sir, actually, I've joined by mobile, so I can't like, and I've written the solution.
Okay, so I'm just asking you like if you can just take a photo of whatever that you have like solved,
Oh,
um,
yes, sir. Just a moment.
and then share like or if you can just share it on the chat over here if it is possible, then I can share your
Yes,
solution
sir.
on
I'll,
as well.
I'll do it. I'll do it, sir. Yes.
Okay. So either you can share your own screen, like you can share the photo, uh, and or if you can use your web camera to show your solution, anything like any way. Like
Oh, yes, sir. Sir, can you see my photo? Hello?
yes, yes, I can see your solution. So can you just rotate it if possible, or I'm
Okay.
not sure. Like it can
Uh,
keep the screen rotation on or something like that. I don't know. It's kind of
o-
it's visible, but it's rotated.
okay, just a minute, sir. Okay. Sir, now is it okay?
Yes. It's rotated in that thing, but if you hold your phone like horizontally, will it auto rotate? Ah, this is okay. Right. Right. Correct. Correct. Right. So how did you so can you explain how you derived these expressions?
Sir, first, like I took the sum of all the forces, like the rolling resistance, grade resistance, aerodynamic, and all these resistances. And then I use the momentum equation, like mdv by dt is equal to the summation of all the forces, algebraic summation of all the forces. And then I simplified it. And then for this WF and WR, I took the uh, like the moment, resultant moment at the R, like the where the tire and the
Right.
ground meet. At that point, I took
Right.
the moment, and
Okay.
then on simplifying, I've got this equation.
Right. 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 Correct. Correct. And what about this maximum tracting force?
So that is just the product of coefficient of friction and the normal force. So that's it. Like mu will be given, and WF is the above expression.
Correct. So so for a front wheel drive and rear wheel drive, what will be the difference?
So for rear wheel drive, the maximum tangential force will be more
For which one?
for a rear wheel.
Okay. Okay. Fine. So so right. So Amey, thanks for sharing your solution. So if you look at the expressions for WF and WR, it also has this FT, right? So
Yes.
you are equating FT is equal to mu into WF or WR. So it already has an FT here as well. So on the right hand side. So you will need further simplification to derive the actual expression of the tractive force, right?
Okay.
So that is something that you can try out.
Okay, sir.
So yeah, yeah. Thanks for sharing, Ameya.
Yeah. Welcome, sir.
So very good. So that's the nature of the reaction forces that Ameya has shared. So yeah. So as you rightly said, we need to take moments to derive the axial reaction forces. So we can simplify it to these expressions. So which is exactly what you derived. And for the maximum tractive force, like for a front wheel drive, the tractive force will be acting on the front set of wheels. So it will be this mu into the front wheel reaction forces. And for the rear wheel drive, it will be for the rear reaction forces. So, so as I mentioned, like there will be a tractive force term over here on the right hand side. So we need to simplify this further. So we get this maximum tractive force expression for the front and rear wheel drive. Sure. So if we now calculate the tractive torque at the wheels and what will be the vehicle speed, if you have to express like in terms of the power source, like the tractive, like the torque that is provided by the power source and the vehicle speed uh, as a function of the speed of the power source. So we can derive some simple expressions. So let us say IG is the gear ratio of the transmission and I naught is the final drive gear ratio, which is like just in front of the differential. So that this total gear ratio and if eta PT is basically uh, this thing I naught is basically the final drive gear ratio. Ig is the transmission gear ratio. Eta PT is the powertrain efficiency. So if TP is the torque output of the power source, let us say either it can be an IC engine or an electric motor or anything. So we can write this kind of an expression for the torque that we will observe at the wheels. And the tractive force will be this torque divided by the dynamic radius of the wheels. So we can derive this kind of an expression for the tractive force at the wheels in terms of the torque output of the power source. So this gear ratio of the transmission is basically the ratio of the input, like transmission input side speed divided by the output side speed. Okay, then if we have to calculate what is the speed of the wheels, so it will be the speed of the power source NP divided by the gear ratio of the transmission and uh, the final drive gear ratio. And if we have to derive the vehicle speed, so we get an expression of this kind of like where NW is the wheel RPM. So in terms of the RPM of the power source, we get like this kind of an expression. Uh, in terms of the wheel radius, the speed of the power source, and the overall gear ratio. Now we'll look at some vehicle performance metrics. Uh, so, uh, so we looked at how we calculate the overall tractive force and what are the different resisting forces. Now, as a result of that, we we are like there is a certain maximum speed uh, of limit of the vehicle. Uh, so considering the different gear ratios that are available, and so for different uh, speeds, like so considering what is the like the maximum power or maximum tractive force that can be supplied with respect to the vehicle speed. So like we can derive the tractive force requirement, and we can also we know, since we know that how the maximum tractive torque varies, like for the power source, like let's say for an IC engine, we know the torque and speed curve, maximum torque speed curve for the IC engine, let us say if that is given, and we also know the gear ratios of the transmission. So then like as like explained yesterday, so in yesterday's session, so we saw how we can superimpose the overall tractive force available versus vehicle speed for every gear. So like we calculate the equivalent torque that is available at the wheels for the certain like vehicle speed. So we can plot the curves for each of the gear. Let us say we have 4 gears. So then we can generate plots like this. Now on this same plot, if we superimpose the curve of tractive force requirement, uh, like basically the overall the sum of the rolling resistance, air resistance, and gradient resistance, the total resistance force, it will be a function of the vehicle speed. So let us say if we plot the variation of that uh, overall resisting force with respect to vehicle speed for different vehicle speeds and for different road gradients, we will get a family of curves like the way it is shown over here for different road gradients from starting from 0 degree, 5 degree, 10 degree, and so on. And for different for different gears. So we see that these curves intersect the maximum tractive force versus vehicle speed curves of the IC engine here. So let us say if like in the fourth gear, like since we want to find the maximum vehicle speed, so zero grade is the like the flat kind of road. So the maximum speed we can define it with respect to what can be achieved on a flat road or 0% grade. So then, so the point where the tractive force required and the tractive force available, they intersect. That is the maximum speed that the vehicle can reach. So, so for that particular road grade, the vehicle can achieve, like let us say this is something about 170 or 180 kilometers per hour that the vehicle can achieve. So we can see that this particular curve intersects over here, and that is how we get the maximum vehicle speed. So this is like for full throttle, like this is the maximum torque versus speed. So this is at full throttle. So this is how we basically get. So how do we calculate this, like these curves? So we calculate like basically the tractive force and resisting forces are in equilibrium. So since these are tractive force requirements at constant speed. So, so this is basically the cruising speed, that the maximum cruising speed that the vehicle can achieve with full throttle on a flat road. So if we have to derive an expression for what is the maximum vehicle speed, we will equate the tractive force with the sum of the resisting forces. We get the expression for total tractive force in terms of the IC engine torque here, let us say, and uh, and we know like uh, the various resisting forces. We know the like road gradient, uh, and so we have a basically a function in terms of like v square. So then this particular term will vary with vehicle speed. So let us say we assume that this rolling resistance force is like rolling resistance coefficient is a constant for now. So then we can derive an expression for maximum vehicle speed, which looks something like this. So because of the quadratic nature, we see that like we get the expression for maximum vehicle speed as a square root of the net resulting tractive force minus minus the rolling resistance force and the gradient resistance. So this is about the maximum vehicle speed. Another important uh, metric, yeah. So before we move on to the next metric, so for the maximum vehicle speed, let us say like we derive the maximum speed as a like the intersection point between the tractive force required and the tractive force available. Those two curves, right? So what if there is no intersection point between the tractive force required and the tractive force available? Right? So then how will we define the maximum vehicle speed? Any guesses? Any like what will be the what will we do in that case? Any answers on that? So Kshitij Verma. So do you know what we need to do if we do not find an intersection point between this tractive force required and tractive force available curve?
Uh, Sir, I think then we'll be using available tractive force to calculate.
Uh, no, in the sense, like, see, I'm like explaining, like, what I mean is, let us say if we have this tractive force available curve, let us say like this, something like this, and like if we have this kind of a curve which actually does not intersect it here at all. It goes somewhere like from below somewhere. So then how will we define the maximum vehicle speed in this case, in this scenario? Can you answer like with respect to this figure? Any cases? Yeah.
I'm not sure.
Sorry?
I'm not sure about this.
Not sure. Okay, fine. Yeah, so it's so since the the tractive force available is kind of like, let us say if this is for zero grade and we define the maximum speed for zero grade with respect to zero grade, then so at this particular vehicle speed, like let us say this point, like look at this point here, this particular vehicle speed. So the tractive force available is actually more than what is required for zero grade. So like because of the IC engine maximum speed limit, we should not actually go beyond this. We should not accelerate beyond this speed. So ideally, like if we extend this curve like somewhere like this, then this would be the intersection point. But we cannot extend this because of the speed limit of the IC engine here. So then, what becomes the limiting factor now? It is the maximum speed limit of the IC engine itself that will define the maximum speed in this case. So, so here then, if there is a no intersection point, then we will just go by what is the maximum vehicle speed achieved at the uh, in the highest gear ratio, like I'm sorry, I mean the highest gear or the lowest gear ratio, and like considering the engine is supplying maximum torque at its maximum speed. So then that will be the maximum speed uh, in that case. So make sense?
Yes, sir.
Okay. Now another important metric which is called as gradability. So anyone of you already familiar with this term? So gradability is basically the road grade or the grade angle that the vehicle can overcome basically at while moving at constant speed. So it's an important vehicle specification, especially like for heavy commercial vehicles or off-road vehicles. It is like defined as the maximum grade that it can overcome over its whole entire speed range. So that's an important performance specification for these category of vehicles. So how do we derive the expression for gradability? So again, we since the vehicle is moving at constant speed, so there is no acceleration. So if we like go back to the equation of motion, so if we equate the acceleration to zero, so then again we will get that the tractive force is in equilibrium with the resisting forces. So on the left hand side, we get the tractive force in terms of the power source torque output, and on the right hand side, we have the resisting forces. So now what do we have to derive over here? We have to calculate alpha. So for a given vehicle speed and for like the full throttle, what will be the maximum grade that the vehicle can climb. So we know the vehicle speed, we know the output torque of the power source, and we also know the gear ratios. So we know basically the maximum torque versus speed characteristic for the like consider we know the tractive force or tractive torque available versus vehicle speed. And for the given vehicle speed, what is the maximum grade that it can climb? So to derive that, we have to basically derive an expression for alpha. So how we will derive that? Uh, so here we just need to do some trigonometric manipulations. So let us say we substitute uh, tan beta is equal to this Fr. So Fr is basically the rolling resistance coefficient. So then we get cos beta is equal to so what will be the value of cos beta if tan beta is Fr? So it will be 1 upon square root of 1 plus Fr square, right? And sin beta will be Fr upon this whole square root of 1 plus Fr square. This so then we will get in this expression. So this like if we divide and multiply by root of 1 plus Fr square, it will be sin alpha into cos beta plus cos alpha into sin beta. So which is same as sin alpha plus beta. So we get this expression like on the right hand side as mg into root of 1 plus Fr square into sin of alpha plus beta is equal to this particular difference. So the left hand side is known and we need to find alpha. So we will calculate the sine inverse minus the beta, so which is tan inverse Fr. So this is the expression for the maximum grade that the vehicle can climb for a certain given vehicle speed in a certain gear for the power, like for the maximum torque that is available from the power source. This is how we can derive the expression for gradability. So any doubts on this? So another performance metric is basically the acceleration performance. So the basically acceleration performance is reported as the time that is required to accelerate between a certain given set of speeds. Let us say from 0 to 100 kilometers per hour at full throttle. So it is called as like commonly called as WOT, which is like wide open throttle. So like if we accelerate at full throttle, uh, then what is the time required to go from 0 to 100 kilometers per hour or let us say 30 to 50 kilometers per hour. That is how generally in industry is reported for different uh, vehicles. So it's an important performance specification. So how do we calculate this acceleration performance? So again, we come back to our equation of motion. Here we express this acceleration in terms of the tractive force and resisting forces. And now what we have to derive is basically the time. So now we have to, yeah, if we just further simplify this expression in terms of like the tractive force and resisting forces, we get that same kind of expression. But now what we have to do to basically to so how will we derive the time required now? Any guesses? Any answers on that? What do we have to do to get derive the time required? So Vinayak, can you answer that? What do we have to do to get the time required to accelerate? Sorry for the disturbance, if at all. Uh, Sorry for the background noise. So anyone has any idea how do we derive the time required? Yeah.
Vinayak, sir is asking some question. Kshitij, Amya, Aishwarya, please answer.
So anyway, basically we so in order to derive the time required, because this is a differential equation, this is a simple ordinary differential equation. So we like so we need to integrate uh, the basically the vehicle speed. So we have an expression for that in terms of like so dv by dt is equal to something. So the right hand side is a function of the vehicle speed, and the vehicle speed is varying with time. So now we can just simply integrate. Yeah, so we can just integrate this expression in terms of like so this so for a certain like the time required to go from a certain vehicle speed v1 to v2, so we can write it as an this expression. So similarly, we can also calculate the distance SA. So like if we for a certain time dt, the distance traveled will be d into dt. So we know so since from dv by dt we know like the expression for that. So then we like multiply by velocity to get this expression. So then this is how we can actually calculate uh, the acceleration performance in terms of either the distance traveled or the time taken to accelerate between certain set of speeds. So this acceleration may not always be easy to perform because the, basically the torque versus speed availability is different for different gears. Uh, so as the vehicle accelerates like from like higher and higher speed, so we also need to have a so in order to calculate this, we need to know where at what speed uh, the vehicle will shift gears, and so we need to perform a certain complicated numerical integration probably to evaluate this integration. So any doubts on this? So so I think it's time a time up for today. I think it's already 10:30. So I think we will stop here for today. Um, so any questions on the part that was covered today? So we basically today we just looked at the uh, vehicle dynamics and how do we calculate the tractive force and the resisting forces. And then how do we use the knowledge of this tractive force and tractive power requirement to derive different vehicle performance metrics like maximum vehicle speed or the acceleration performance or the gradability. So these are the like important vehicle specification like metrics. And for designing transmissions, so generally manufacturers or like vehicle manufacturers will set certain uh, performance requirements, and those have to be met like by the entire vehicle along with the transmission. So these are important metrics based on which we can further design the transmission. So it's important to know these metrics. So that's the reason I have covered this in today's session. So I hope you find this session useful. Any questions or comments? So if not, I think we can close for today. And so I'll see you in the next session. So I will let you know exactly when the next session will be. I think most likely it may be on Friday morning. So is Friday morning suitable for everyone? So I'm asking all of you. So is it like Friday morning time? Is it okay for all of you for the next session?
Sir, at what time on Friday?
Friday, maybe same time around 8:30 or so. Is that okay for all of you?
Is it possible if we start a little late, like 9 o'clock maybe?
Yeah, that is also okay.
Okay.
Yeah, sure. Anyone else has any concerns like any is this time works for all of you on Friday morning?
Yes, sir, it's fine. 9 a.m. is
Okay,
okay.
okay, fine. Sure. So I think then we can meet on Friday for the next session. So Saturday, Sunday, I won't be available. So after that, I think we'll meet directly in the next week itself. Uh, so by like, what is the like so your classes are up to what date? Like when are your classes getting over? So can someone tell me like what is your last like working day or last day of instructions?
Sir, it's 15 April.
15th of April. Okay, fine. Sure. So I think we will try to wrap up this thing probably by first week of April or so. So I will let you know how we will like. So for now, we'll just have the next session on Friday, and further I will let you know afterwards. So I hope that's okay. So like,
Sure, sir.
so you have exams and practicals or anything before that, like in April?
No, sir.
Okay. So up to 15th April, you are like kind of free to take so we can have sessions till like in the first week of April as well, right?
Yes, sir.
Okay, okay. Sure, sure. Thank you. Thank you all. So we'll stop here for now.